Swayam Prabha. Digital India. Educated India.
Welcome back. So, today I am planning to do some examples on the induction motor, because we have done quite a few number of formulas on torque, speed, equivalent circuit and so on. So, because I think it is better to do some examples before we do some other things to get this idea clear. And again, my reference book is Professor Pai's Power Circuits and Electromagnetics. So, the first example that I am having here, I have a 3-phase induction motor, and it is a 2-pole induction motor, and its 3-phase voltage is 866 volts. Deliberately chosen this number Y connected. So, the idea is that when you do 866 by root 3, it comes out, it is actually 500 into 1.732. So, when you do 866 by root 3, you get a nice number called 500 volts, which is the per phase voltage. And let us take this motor at 50 hertz. We could take it at 60 hertz also. It is in fact we can do both 50 hertz and 60 hertz if we feel like. And I am given that its stator resistance is 0. So, stator resistance is 0, its impedance stator leakage reactance is 0.5, and its magnetizing impedance is say 50 ohms, and I am sorry, the leakage reactance of x 2 dash, it is also, so this is my x 1, this is my x 2 dash, this is my x m, and the rotor resistance is 0.1 ohms, again referred to so 0.1 ohms divided by slip, R 2 dash is 0.1 ohms. And here I am applying 500 volts. So, this is the equivalent circuit for A phase. I am taking a reference voltage as a reference voltage as A phase reference is taken as the reference voltage. So, therefore, the angle is 0. All other things I have marked here on the equivalent circuit, all parameters are marked on the equivalent circuit. So remember, this is my this is my leakage reactance X1, this is my leakage reactance X2 dash, R2 dash is given as 0.1, slip is of course S, and the magnetizing impedance is Xm. Now our I2 dash flows here, and if you recall the power which is transferred through the air gap. So, the power which is transferred through the gap is 3 times magnitude of I2 dash square by into R2 dash by S. So, this is the power which is transferred through the air gap to this resistance, out of which rotor loss. So, the rotor loss is 3 is for the number of phases, remember that, I2 dash square R2, and so the power which becomes available for doing mechanical work is basically 3 I2 dash square R2 dash by S minus, better pull it at the center, minus 3 times, because the balance thing. So, the loss, everything is in terms of power and loss per phase is going to be the same, and so this is 3 I2 dash square R2 dash 1 minus S by S. So, in all the calculations that we are going to do today, this I2 dash calculation is going to be very important, because we will have to calculate this mechanical power, and we know that the mechanical speed for a 2 pole machine is 1 minus S times of the synchronous this. So, speed. So, for 2 pole machine working at 50 hertz, this is going to be 100 pi radians per second, or I will just write it as 304, actually 3.1415. You can expand it, it is anyway, pi is an irrational number, but roughly speaking it is 314 radians per second. And so, the torque which is generated in the machine is going to be P mechanical divided by omega m, which is 3 I2 dash square R2 dash by S into 1 minus S divided by omega m, which is 1 minus S by omega S. We have done this, but it is I like to be doubly sure. I do not usually like to remember the formulas, and I really do not like to remember the formulas. Instead, I prefer to do it once more, and repetition makes us perfect. So, really speaking, that 1 minus S gets cancelled out, that is the important point which I am trying to emphasize, and therefore, the torque which comes out is 3 I2 dash 3 I2 dash square 3 I2 dash square by omega S R2 dash by S. So, it is actually pretty simple to given a slip, our methodology is going to be calculate, if we know the slip, just calculate R2 dash, plug it in here, and you have got both the torque and the speed. So, that is going to be the simple methodology that we are going to follow. Now, in this particular question, so far I have not specified the slip. So, now let me specify the slip as 0.05. So, that means 5% slip. So, this value is in per unit. So, the slip is 0.05. So, if I take 0.05, then this will become how much? 0.1 divided by 0.05. So, 0.1 divided by 0.05 will be 10 divided by 5, which will be 2 ohms. This resistance here R 2 dash by S will be replaced by 2 ohms. So, let us do that. Let me pull this circuit down, and now that I have no, I do not need all this. Now that I have specified this, this will become this number will become 2 ohms. Now, what are the two tasks that we have to do? We have to calculate I 2 dash, and once the I 2 dash is known, then we can go ahead and calculate all of this. So, we will take two approaches to do it. In fact, we can take three approaches to do this, solve this problem. So, approach 1, the most common one which I recommend, which I have taught in the last class, go for Thevenin's equivalent circuit. Go for developing the Thevenin's equivalent circuit. This is most generic approach, because in general slip is unknown quantity, and if you write a you want to plot a torque speed characteristic, then once you have written down this equation, then you can just keep changing the slip value. If you have written the Thevenin's equivalent, how will the Thevenin's equivalent look like? You will have this as the V Thevenin, this will be your Z Thevenin, which in our case will be X Thevenin only, because when we are looking from here, you cut this thing out as the load, all the rotor side you cut it out as load, and then you are looking inside from this. So, you will short circuit this voltage. So, this impedance and this inductance will come in parallel, and two inductances coming in parallel will create a new inductance only. It cannot be combination of RLC, it will just be inductor. So, therefore, it will be X Thevenin, and then this when this is taken out, current will flow through this series circuit, and a proportionate voltage which is developed here, which is J 50 divided by 50.5 times 500 volt, that will turn out to be V Thevenin. And then once you have got this Thevenin's equivalent, then what are you going to do? Your rotor circuit, rotor equivalent circuit, you will again connect back here, which is 2 ohms. So, this is going to be my approach 1. Approach 2 is, let us call this as figure 1, let us call this as figure 2. So, approach 2 is attack figure 1 as it is. But the problem with that approach again is, for this problem it will work out fine, but if I ask you for 2-3 values of slip, then every time you have to attack from ground 0 everything, which does not work out very well. So, therefore, better to train ourselves for approach 2, but when only one slip is given, better to train ourselves for approach 1, but if only one slip is given, approach 2 is also fine. Approach 3 can be, though I have not recommended it, but you can see when you are doing back of the envelope calculations, not writing programs and things like that, and in this particular example, if you see that this 50 is quite much higher than 0.5 leakage impedance, and this voltage is going to be dominated by the voltage across this is going to be dominated by this J50 only, and this is much less. So, almost whole of this voltage will come across here, and when you are looking at Thevenin's impedance, it will be practically be dictated by this shorter value, because this is too much longer. So, when you connect a very small impedance in parallel with a very large impedance, then you know that, right, 1 by Z1 plus 1 by Z2. Suppose Z2 is, this is equal to 1 by Z equivalent in parallel. So, 1 by Z1 plus 1 by Z2 is 1 by Z equivalent when in parallel. Suppose Z2 is much larger than Z1, then this number is much smaller than 1 by Z1. So, approximately it becomes just 1 by Z1, that means Z equivalent will be approximately equal to Z1. So, looking at these numbers, it suggests to me that even approximate approach should work here. Even the approximate approach should work in this problem. Okay. So, let us start with approach 1, Thevenin's equivalent circuit. So, first thing let us calculate, let us for V Thevenin let us write down the circuit. So, this will be 500 angle 0, you will have J 0.5, this is J 50 and this, and the open circuit voltage is to be calculated across this. So, therefore, the V Thevenin will be J 50 divided by J 50 plus 0.5 times 500 volts, which is 50 divided by 50.5, 500 volts, and this is going to be 495 volts. Let us just check it up once. So, I have 50 divided by 50.5 into 500, which is 495.05 volts. So, V Thevenin, as I had expected given the looking at the numbers, this and this is close by, only 5%, 5 volts difference. So, 5 volts over 500 volts is 5 over 500 into 100 is 1%, means if I use approximate circuit and just take V Thevenin as 500 volt, approximation there will give me a voltage error of only 1%. Okay. Now, let us calculate the X Thevenin. So, for calculating X Thevenin, what we have to do? We have to take the parallel combination of, since this will be short circuited, this will be short circuited. So, you are going to take a parallel combination of 0.5 and J 50, 5 and J 50, and so this is going to be J 0.5 into J 50 divided by J of 50 plus 0.5 means 50.5, which is 25 divided by 50.5 J, which is going to be 25 divided by 50.5 is 0.495 ohms. Now, again as I had told you that looking to these numbers, I can easily say that it will be dominated by this 0.5. So, again a small error only is there. So, therefore, approximate approach, when we will consider that, should work out well. So, in approximate approach, what we will do is, I will come to that later on. Let us finish what we have already started. So, I have now simplified this circuit, right. I have this thing, Thevenin's approach is pasted here. So, this is 0.495 ohms and this is 495 volts, 495.05 angle 0 volts. R2 dash by S, because the slip was given to be 5%. So, therefore, it is replaced, already been replaced by 2 ohms, and in this equivalent circuit what happens? What you are able to directly monitor is this I2 dash, which is all we want. So, therefore, we will directly know what this Thevenin's equivalence will supply is I2 dash here, and we can compute I2 dash as 495.05 divided by sum the two resistances. So, it will be these two resistances will go in series and then they will come in parallel with I am sorry, this is not resistance, this is inductance. I should write J. So, these two inductances will go in series, which will give me a net inductance of 0.5, 0.9495. So, 0.995 0.995 minute, and nothing in series with this 2 ohms. There is only one resistance in series with 2 ohms, and this will be, actually speaking, I am only interested in magnitude of it. So, if I am only interested in the magnitude of I2 dash, since I am only interested in magnitude of I2 dash, that is going to be equal to 495.05 divided by square root of 2 square plus 0.995 square. So, this is what is going to be my I2 dash. So, let us calculate this. 2 square is 4 plus 0.995 square is this point double. So, it comes out to be 4.990025, and I should take square root of it. So, if I take square root of it, it is 2.23 233 sorry 2.233 and 495.05. So, do 1 by x multiplied by multiplied by 495.05, and that comes to around 221.61 amperes. So, therefore, our torque, and we have already written down the formula for torque, it is this. Let me borrow it. Down. So, you can see it is not it is pretty easy to work out induction motor problems. In fact, usually it turns out to be quite a scoring exercise. 3 into 221.6 square divided by omega s for a 2 pole machine. I have already calculated it as 314 radians per second into R2 dash by S. We have already calculated that to be 2 ohms. So, therefore, this number will have to looks like it is going to be a large number. So, let us see what it comes out to be. 221.6 square divided by 314 into 3 into 2. So, that is going to come out to be that is going to come out to be 938.34 Newton meter. So, if the answer is find the torque at speed at 0.05 this thing, then this answer suffices. Now, if suppose also the question is asked is find the 3-phase input power. Suppose in addition this is also asked for, then the power factor you can calculate from here. This we have already written down this as 2 ohms and J 0.995 this thing. So, tan phi is x by r, which is 0.995 by 2. So, let me just do that, 0.995 divided by 2, and then its inverse, its inverse. So, inverse tan. So, that will be, that is the tan inverse, and that turns out to be in degrees, this phi will turn out to be 26.45 degrees lagging. Because why lagging? Because it is a RL circuit. So, therefore, the current is going to lag by 26.46. So, if I take cos of that, so cos of phi is 0.895, you can call it 0.9 lagging. So, this is my power factor. So, if you know, you ask me what is the find the input power. So, 3-phase input power will be √3 VL IL cos phi, and so √3 VL is how much? 866 volts. Current is how much? 221.61 ohms. 221 this the am I right in saying that this is the 3-phase input power? I think so, yes, I think so. So, you may be thinking what was confusing me for the time being, but the thing that was confusing me, which was 2.1.61 into cos phi, which is 0.895. See, the thing is, what was bothering me was that to calculate the input power, I was calculating it from here, this equivalent circuit. So, I was just thinking whether it is a correct thing for I was just thinking whether this is correct, in the sense that I have done a Thevenin's equivalent of this. So, if I look at complex power, it is correct if as far as what is going on into the rotor circuit, there is no problem, because I am using I2 dash. as far as active power is concerned, answer is again correct, because there is only dissipation in the rotor part. The stator resistance has been anyway neglected. So, therefore, there is only dissipation resistive element in the rotor part. So, whatever is consumed in the rotor part. So, again this equivalent circuit works. Only place where it does not work is that this tells me what is, it does not, if I look at input power, reactive input power, then that reactive input power is not just what is being consumed here. I can calculate whatever is being consumed here, but then in addition to that there is something which is consumed here and something which is consumed here. So, it is correct at this boundary, but when I look at it here, I should add this current component, then get this current component, and so the phase angle will slightly change without altering the real power, because the resistive part is only in the rotor circuit, but it will definitely alter a bit it will definitely alter a bit the power factor seen here. Power factor seen here will be a bit different. So, the reactive power component will be changed a bit, but the active power component will be same, because resistance is in our case present only in the rotor side, the load. So, let us calculate this. This is going to be 1.732, I am sorry, 1.732 into 866 into 221.61 into 0.895, and then I am going to divide it by 1000. I am going to divide it by 1000, and that will give me 297.493 kilowatts. So, this is the amount of input power which is going, and this 3 phase is again, this input power is nothing but what is going in the air gap, because whole of this goes into the rotor side. So, if you ask me what is the mechanical power, then it is just 1 minus s of it, because I 2 square R 2 dash, as I explained to you, goes into the loss I 2 dash per phase basis, I 2 dash square R 2 dash by S goes and all that. So, we did all that calculation. So, therefore, this thing will turn out to be into 5%. So, 0.95. So, therefore, 2.619 kilowatt is the mechanical output at this mechanical output power, and the mechanical torque is going or the torque is going to be this particular value. So, this completes my approach 1. This completes my approach 1. Now, let us do the same problem by approach 2. So, what I have to do in approach 2, and usually when you are dealing with exams, it is better to solve in one way and cross check it by another way, so that you are sure that your answers are matching. So, let us do the approach 2. So, this is 2 ohms. So, now what I have to do? I have to take 50 in parallel with 2 plus j 0.5 to 50 in parallel with 2 plus j 50 in parallel with 2 point this thing, and then that should come in series with j 0.5, and this value is the z net. I will not do it, I think it, because again I am going to get the same number. So, So, this is something I am just leaving it to you as fill in the blanks, and once you have done that, then you will get. So, even now I feel that our initial approach was only better. I will do the approximate thing, I will do that. So, now I will get 500 divided by Z net, I will get I 1, then I should get, let us call this as V m. So, then I will get V m as 500 angle 0 minus j 0.5 times of I 1, and I will get V m. Once I have got V m, then I can calculate I m as V m by j 50 and subtract this from I 1, subtract this from I 1. So, what will I get? I 2 dash. So, I 2 dash will become I 1 minus I m. Once I have got I 2 dash, then all other again my all those things are simplified. But you can see that this way seems to be more cumbersome than the simple way Thevenin's equivalent circuit. Step by step approach more straightforward. Okay. Now, let us do the approximate one. In approximate approach, approach 3, which is approximate, this of course depends upon the type of data. In this case, I have already shown you that it should work. What we do is, just like transformer, we will assume that this x m can be shifted here j 50, and then this inductance of leakage inductance of 0.5 ohms of this and of the x 2 dash 0.5, and then this R 2 dash by S, which is 2 ohms, and this 500 this 500 volts, they come in, they come like this. Since we are only interested in I 2 dash, so we can write I 2 dash as 500 divided by 1 plus j, sorry, 2 plus resistance is 2 and the series in 2 plus j 1, and if you compare it with here, not much difference, right, not much difference, 2 plus j 0.955, here it is 2 plus j 1. So, here we are writing it as 2 plus j 1, here it is 2 plus j 0.95, and here we are writing it as Thevenin's equivalent voltage as 495.05 volts, but in the approximation we will just take it as 500 volts. So, therefore, I can write this as 500 divided by square root of 5 if you are looking at the magnitude of I 2 dash, and this is going to be this is going to be this comes out to be 223.60 amperes. Compare this with 221 amperes, and I think again I will not solve it further. This 221 has become 223, R 2 dash by S is same. So, if you calculate this here, okay, let us do it for one sake, the fun in knowing the exact values. So, let us solve this again. So, let me pick this up here, but again I will not probably next time solve the full approximate circuit, this time I will just do for the talk. So, I will get this as 3 times 223.6 square divided by 314 into 2 ohms, and so this now let us calculate this. 3 times let me do something 223.6, let me square it first. So, I square it, divided by 314, then multiply it by 6, and this comes out as 955.35 Newton meter. So, how much I had calculated earlier? Earlier I had calculated it as 938.34 Newton meter. Now, it has come out as 955.35 Newton meter. This much this is okay, this much 935, 955, 20 is difference over 1000, around 1000 base, that is okay. This much approximation will cause error, this thing, but if you are in a hurry, you want to do the, so to say, back of the envelope calculation, this number seems to turn, this numbers is quite acceptable. And so, if you this time input power, so this time let me calculate the mechanical output power. I can just multiply this by the speed, which is omega s is 314 into 1 minus s is 0.95. So, let us see how much is this P mechanical output. Just for the heck of it, I am calculating this. So, I will get this as 955.35 into 314 into 0.95 and then divided by 1000. So, I get it around 284.98 kilowatt. Let me see what I had calculated earlier. So, I had calculated it as 282.619 kilowatt, and this number is again 284.98 kilowatt. So, you can see that if the magnetizing impedance is much larger than the leakage impedances, especially the much higher than the leakage impedance which is associated with the stator winding, then the approximate approach can be used to avoid calculation of the Thevenin's equivalent circuit. That is the main takeoff of this example, other than the fact that we also did one solved example. Okay. Now, let us go to one more problem. I think we have milked this problem enough. So, we should now choose another problem and see what it can offer us to us. So, let us calculate in the same example, in the previous example, calculate P max maximum torque and the slip, so at which it occurs. So, let us try to work this thing out also. So, in other words, we have to calculate T max and we have to calculate S max. S max is the slip at which maximum torque occurs. So, S max was, if you remember, S max was given by, so the R2 dash by S max was to be equal to the impedance of all the remaining elements in series. So, in the Thevenin's equivalent case, it is going to be R Thevenin it is the impedance of magnitude wise J times x Thevenin plus it is the magnitude of this, which is same as square root of R Thevenin square. See, the end of the last class, if you recall, we had done a very large derivation for it. We took the torque expression, then we took the torque expression, then we took its derivative and set it to 0, then we found out the S, then we found out that torque which comes out from it, maximum torque that comes out of it, because maximum torque will correspond to a stationary point. And then I said that second derivative of it should be negative, you should check it out. But even if you plot it also, you see that between 0 to 1 where I had taken that S max, a MATLAB plot also if you do, you can see from the plot that it is a unimodal function, there is only one maximum sitting there, and that is what exactly I had that is what I had exactly calculated. So, the S max is, and this was the condition which was obtained from that derivation. So, we just need to plug down these values. So, R 2 dash is given to us as 0.1 ohms, and R Thevenin we calculated as R 2 dash by S is 2 ohms, but the R 2 dash itself is R 2 dash itself is just is just given in the problem as 0.1 ohms, and x Thevenin, let us come here, let us come to the Thevenin's model. The x Thevenin we have calculated as I am sorry, x Thevenin is sitting here, it's 0.495 and x 2 dash is 0.5. So, R Thevenin is 0.1 square and this is 0.495 and x 2 dash as that I mentioned, where I need to go back once, x 2 dash is 0.5, x 2 dash is 0.5. I am not a great number cruncher, some people are great number crunchers, but let us still work it out, no problem. 0.1 divided by under root of 0.1 square, I will write it approximately, the other one is also 0.1 square, 0.995 square. So, I am just taking it as 0.1 square. So, it is 0.1 divided by under root of 2 into 0.1, which would come out to be so the S max will come out to be so 1 by root 2, which is coming out to be the point I am sorry, I made one mistake, I am really sorry. R Thevenin was 0, there was no R Thevenin, because the let me show you, I do not know where did I pick this R Thevenin, it is just J, you see here, it just this Thevenin's impedance is just 0.495, it is in the J. So, it just connects with this, and in this simple example, because the stator resistance has been neglected, rotor resistance cannot be neglected, otherwise you will not get R 2 dash by S. So, the stator resistance just creates a bit of loss in the heating, and therefore, you are able to neglect it. But even though the rotor resistance may be of small value like the stator resistance, when it is divided by S and the slip is small, R 2 dash by S will become a large quantity. So, therefore, the rotor resistance cannot be neglected. Stator resistance for our sake of simplification the authors have given is have neglected the Professor Pai has neglected the stator resistance, so to say, in this book. So, and same thing happens in other books also. I mean, there is nothing different about it. So, I made that mistake. I am sorry. So, that is why I have to redo this. This is not there. So, then I do not need to do any. This will be 0.995 square, and so if you calculate this, it is going to be it is as good as 1, right. This 0.995 square, 0.995 is as good as 1. Sorry. So, approximately 0.99 is approximately 1, 1 square under root is 1. So, this is approximately S max is going to be equal to 0.1, and what is the unit of S max? It is per unit value, dimensionless quantity, because it is a ratio of the difference of the speed to the ratio of the difference of the speed to the maximum speed, right. So, therefore, 0.1 ohms, not ohms, 0.1 per unit. So, now S max is known to us. We had also calculated that we can now once we know the X max as 0.1 ohms. So, we have 495 sorry, Thevenin's voltage is how much? We can use directly the formula also, but I am going to use the Thevenin's equivalent circuit, and the Thevenin's equivalent circuit is 495.05 volts. Let me take this value here. Let me take this and modify this. So, these two elements do not change. Okay. This is leakage reactance of the secondary winding referred to the primary. So, this also does not change. R2 dash by S, this thing R2 dash by S, this was at slip 0.05. So, it came to 2 ohms, but now it is R2 dash by S max, which is 0.1 divided by, what is the S max we calculated? S max we calculated as 0.1 itself, right, approximately 0.1. So, therefore, 0.1 by 0.1 is going to be equal to 1 ohm. So, therefore, this circuit is this voltage J 0.995 and this 1 ohm. So, I2 dash is going to be approximately 495 by 0.5, J 0.995 for the sake of simplification in my discussion, I will write it as J1 plus 1, and even this 495 point, this I will write it as 500, just so not so the so just to keep this is like just solving the approximate circuit. So, 1 square plus 1 square 2 square. So, magnitude of the impedance is root 2 and the angle is minus 45 degrees lagging. So, this is going to be, so if you say 3 I2 dash torque max R2 dash by S max divided by omega s. So, this is 3 I2 dash square will be 25 into 10 to the power 4 divided by 2. R2 dash by S max is 1 and omega s is 300 and omega s is 314. So, this will, let us calculate this. This comes out to so this comes out to 1194.26 Newton meter. So, it is a bit more than it's a bit more than our full load torque. The full load torque we had calculated the full load torque 938 Newton meter, and the maximum torque is 1100 or approximately 1200 Newton meters. So, that's wonderful. So let's stop here for today, and we will continue in the next class. Thank you.